Okay, and now moving on to the actual exam question. So we've built this big expression which gives us our answer, but really these questions are full of all these different terms and we have to interpret them in the right place. So in practice, what you might have done is set up the system like this and solve the question with arbitrary variables in place to keep it messy and then plug in your values later. You could, of course, worked everything out we did in the last video with the actual numbers in, but I would recommend when there's this much algebra, it just looks a lot neater and you're less likely to make mistakes if you do wait until the end. The only downside to that is when specifically the angle is 45 degrees, cos theta and sine theta are going to be the same thing, so things are going to cancel out. However, that's why this question is only 8 marks. We can persist, and so what I will do is just plug the numbers into this question as so, shows how to find RW, which is a step, and then prove that that's the right answer. But of course, do have a go if you would find it easier starting the whole question by drawing this diagram and having the numbers in to begin with, although I'd recommend, and I'm a third-year physics student, so maybe this type of question I know quite well, to do everything with variables before you plug in numbers. It helps a lot. Okay, so we're told that the mass, so what we call big M in the last question, was equal to 35 kilograms. The mass that moves in direction X and is determined by that is 70 kilograms. And the ladder is inclined at 45 degrees. So 45 degrees is that. We're given that mu G is equal to 1/2, mu W is equal to 1/3. And L is equal to 7, sorry. Okay, so we've pretty much, in terms of getting a numerical answer for X, we've got mu W, we've got cos theta, sine theta, we've got M, and we've got big M, and we've got L. The only thing we're missing is this thing, RW, which we have already solved for a few times, but we now have to use the other constraints in the system to build a set of simultaneous equations and find that. Okay, so what do we know in terms of finding it? Well, we already have our two equations that we did earlier, linking these things. So FW equals mu dBl RW and FG equals mu G RG. But there's already 4 unknowns in this thing, because remember we're told what mu G and mu W are, so only FW and RW, FG and RG are the unknowns. If we have 4 unknowns, we need 4 equations to solve them. So what else can we do? Well, 4 equations, we need 2 more equations. Fortunately, there are 2 more dimensions in the question from which we can evaluate. And we know specifically that this beam is not just balanced in its moments, it's not just not rotating, it's not flying upwards, and it's not flying sideways. So we know, considering all the forces here, so if we just, maybe with a highlighter go on, we have a force there, we have a force there. That's not a very good color. Let's do it in a different one. Force there, we have a force there, we have 2 forces down, and we have a force there, and we have a force there. So we have 6 forces in total. So we have, clearly, if we consider resolving now along what we might traditionally call the X direction, we should have the RW and FG must be equal because it's not moving. So we have RW is equal to FG, that's our third equation. And finally, let's resolve along the vertical direction. So we must have this plus this is equal to RG plus FW, the two downs and the 2 ups. So we have FW plus RW is equal to big M plus little m G. And again, I'm going to do everything just abstractly with no numbers put in because I think that makes it easier and prettier. Okay, so now